All right, good morning. Is there anybody who has just joined the class and doesn't have the syllabus? Okay, I didn't think so. All righty, today we're going to talk about fluid mechanics, in particular hydrostatics. And on Wednesday, then, we're going to finish chapter 1 by talking about fluid dynamics. For your homework, you have homework that's due on Friday. And problems 2, 6, and 7, you should already be able to do. They're biomechanics that we talked about on Friday. 16 and 17 we'll talk a little bit about today. You probably won't get to 33, 40, and 42 and be able to say much until Wednesday. So I would encourage you to get working on those. You can bring questions on Wednesday, but we'll probably won't talk about the last 3 problems until the end of class on Wednesday, since we'll cover that material first. So it's a little bit of a short time span to get those last few problems done, but you can always read ahead and then work the problems on your own. All right, any questions from last class? Okay, in that case, let us begin. And I want to start with a problem from the book, problem 1.4. And 1.4 is one of those estimation problems. So it says that estimate the density of water. We're going to be talking a lot about density and pressure today. So the density of water, you have oxygen and 2 hydrogen atoms. The oxygen nucleus contains 8 protons and 8 neutrons. Hydrogen contains 1 proton and no neutrons. So let's see if we can do that. And by the way, if you ever need any physical parameters, there's Appendix O in the back of the book that has things like the mass of a proton. So if you need that information, it's here. All right, so estimate. When you see that word estimate, that means we're going to try to just sort of get a rough approximation. We're not trying to get the density exactly. Let's see if we can just estimate it roughly. And let us imagine water. Water always looks like Mickey Mouse. And it has a distance from the center of the oxygen out to the center of the hydrogen of about 0.1 nanometer. Or in other words, it's about an angstrom. That's roughly the size of atoms. So water is not a solid, but the atoms, the molecules are packed together just about as tightly as they can be to make a liquid. So we're going to imagine that each molecule is inside this box. Or cube, really. And how big is that? Well, you can imagine it would be 2 of these 0.1, so maybe 0.2, but there's going to be a little bit of space between the molecules. They're vibrating around. So I'm going to roughly estimate it as 0.3 nanometers on the side. Now, what's density? Density is mass per unit volume. So rho, Greek letter rho is a symbol for density, is going to be mass per unit volume. And the mass is going to be, well, let's see. There's 8 protons and 8 neutrons in the oxygen, so that's 16. Plus 1 proton each for the hydrogen. That's 18 altogether. Protons and neutrons, electrons are negligible. Times the mass of a single proton or neutron, they're just about the same. That's about 1.7 times 10 to the minus 27 kilograms. That's the mass that's in the box. The volume is just going to be a cube, 0.3 by 0.3 by 0.3. 0.3 nano, 10 to the minus 9 meters cubed. Okay, we're almost there. 18 times 1.7, that comes out to be about 30, times 10 to the minus 27, divided by, well, 0.3 times 0.3 would be 0.09, times 0.3 would be come out to be about 0.027, and 10 to the minus 9 raised to the 3rd power, well, with your rules of exponents, 10 to the minus 9 to the 3rd would be 9 times 3 times 10 to the minus 27. And lo and behold, the 27ths go away, and you get 30 over approximately 0.03. So that comes out to be a little over 1,000. 1,110 kilograms per meters cubed. Is roughly what we calculate for the density of water. Now, if you look it up in a book, what do you get? Well, if you look up water, you get about 1,000 kilograms per meters cubed. That's the density. And we'll be using this density for water over and over, so it's a handy number to remember. There's a couple ways you can write this besides 1,000 kilograms per meters cubed. If you do your conversions, you'll find this is the same as 1 gram per centimeter cubed. A centimeter, it's an old-fashioned unit. It's a 1/100th of a meter. Again, the metric people like us to use units that go in factors of 1,000, so the centimeter is going out of style. But basically, there's 100 centimeters per meter, and if there's 100 centimeters per meter, that means there's 100 to the third power, or there is 10 to the sixth centimeters cubed per meters cubed. This is a problem I often see on homework. People make a mistake. They think they're going to convert from centimeters to meters, and they just use a factor of 100, but it's cubed here. So that's a million, and a factor going from kilogram to gram is 1/1000th. So you end up getting, or 1,000, so you end up getting a factor of 1,000. So the 1,000 goes to 1. There's another way you can write this. You can write it as 1 kilogram per basically 1,000th of a meters cubed. And 1,000th of a meter cubed is a liter. So there's essentially 1,000 liters is 1 meters cubed. So the way to remember that is your liter bottle of pop, it's kind of a silk tube like this, and your 1 meter cube is like that, and you can put about 1,000 of those liters bottles of pop into 1 meters cubed. So 1 kilogram per liter is just a handy way to remember the units for the density of water. Okay, so we're often going to be comparing the properties of water to the properties of air, because these are the two main fluids, basically, main substances that we live in. Our bodies are mostly water. We live in and breathe air. So the density of air is a lot less. It's about 1.2 kilograms per meters cubed. And what's really important is the ratio of these two. Water to rho air. And that ratio comes out to be about 830. So water is a lot more dense than air. And that's going to have implications for life. Now, there's another difference between air and water besides just the density. And that is how compressible it is. Water is, all these molecules are packed in about as tight as they can get. So if you start squeezing, applying pressure to water, you can't change its volume very much. Water is essentially incompressible. Whereas air, if you just look at the ideal gas law from chemistry, if you increase the pressure, you're going to decrease the volume. You can squeeze air, you can compress it, and make its volume much smaller. So that's another difference. Besides their density, is air and water have very different compressibilities. Now, if you want to learn more about the relative properties of air and water, I suggest this book by Mark Denny called Air and Water. A long time ago, before I think I was co-author on the textbook you're using, I used this book in this class because it's a very good book. It's written more from a biology and physiology perspective as opposed to physics. But it goes through all the different properties, density, compressibility, and then properties like viscosity we'll talk about Wednesday, and to electrical properties, to properties of sound propagation, and compares air and water and the implications that has for life. So, again, I recommend a lot of books. I expect you to read them all. Hope that you'll occasionally read one or two, or at least help through. Okay. Now, the other thing we're going to be talking about today is pressure. And so what's pressure? What would be the definition of pressure? Who knows that?
Force applied over a certain area.
Force per unit area, exactly. Per unit area. So the units of force are newtons, and the units of area are going to be meters squared. So newtons per meter squared. And there's a name, just like a newton is a kilogram meter per second squared, there's a nickname people give for a newton per meter squared, and that is the Pascal. Another famous scientist. And this brings me to one of my favorite jokes. Einstein, Newton, and Pascal were all playing hide and go seek, and Einstein was it. So he had to cover his eyes and count to 100 while Newton and Pascal went off to hide. So while Einstein was counting, Pascal ran off and found a really good hiding place, and he thought, oh, Einstein will never find me. But Newton just stood there. He took a piece of chalk and he drew this box on the ground. And then he just stood there next to Einstein. So Einstein got up to 100 and looked up. He says, Newton, I found you. You're now it. And Newton said, no. He said, you found 1 Newton per square meter. You found Pascal. So anyways, that's a good way to remember what a Pascal is, just in case you forget. But we're going to be using lots of different pressures, units for pressure, and Pascal is one of them. Another is the atmosphere, which you see a lot more in chemistry classes. 1 atmosphere, which is roughly the pressure, air pressure here in this room, is going to be about 10 to the 5th Pascal. So about 100,000 pascals. Now, in air, the air pressure varies with height. So one of the reasons why the air pressure varies with height so much is air is very compressible. And you have all this air pushing down on top of us. So basically the pressure is some pressure at the equator essentially. So this essentially P0 here is basically 1 atmosphere times e to the minus y over lambda. One of the things we're going to be talking about a lot in chapter 2 is this exponential function. I assume you've all seen it before. And lambda here, the Greek letter lambda, is a length constant that describes how pressure varies. So when you go up 1 length constant in height, the pressure falls by e to the minus 1. So that's 1 over e. E is around 2.7. So I think really roughly it's a third. So the air pressure will fall to 1/3 of its value at the equator, 1 length constant up. Anybody have a rough idea what that length constant is? I think it's going to be meters, or thousands of meters, or millions of meters. Well, it comes out to be roughly 8,400 meters. So you don't see much change if you just go up the steps 10 meters. But what else in this world has a height of roughly 8,000 meters? Well, the tallest mountains, Mount Everest, for example, is pretty close to this in height. So that means you go up on the top of your highest mountains, your air pressure is down by about 1/3, and that's why it's so hard to breathe. You don't immediately die. It's not like you suffocate immediately, but you certainly have physiological issues if you go up to the tops of mountains, and that's why people have to use oxygen up there. And even if you're up high, but not necessarily this high, say up in Denver, there's a noticeable change in air pressure as you go to those heights. In fact, that's one reason why airplanes are pressurized. Airplanes are pressurized because they fly up above these sorts of elevations. And if they didn't pressurize, everybody would be at low, breathing very low air pressure, and they'd have problems getting enough oxygen. So the fact that you fly in these big airlines or pressurized cabins are because of this issue. Another issue that's kind of funny is that one of the limits of how fast we can build tall buildings is the speed of elevators. And you can't make elevators go too fast because that would create an almost instantaneous change in air pressure. And our ears are subject to the outside pressure, and on the other side of the ears is in our sinuses are usually in equilibrium. Usually the pressure equilibrates, but it can't happen real fast. So if you have elevators that go up real fast and very high, say 100 stories up in a big skyscraper, you care the limiting factor on how fast you're going to make those elevators go is ultimately going to be people complaining about ear pain on the ride. So it's one of these physiological factors that has a sort of an interesting effect on people. Okay. Questions right now about pressure and density so far?
What's why?
Y would be height above sea level, basically. One thing I do want to point out is that the Greek letter rho is usually for density and P is for pressure, and they look very similar, especially on the chalkboard. And so you have to kind of pay attention. This little tick here at the beginning of the P is kind of your clue. Don't get those two mixed up in your notes. P, pressure, density, very different things. Okay, I'm going to erase this, and then we're going to do a little mathematical analysis and derive one of our first differential equations describing we're going to do this kind of analysis over and over, and it's not because I necessarily just want to show you a derivation, but the derivation really gives you insight in what's happening. So what we're going to do is we're going to imagine we're out in the lake, and we're going to look at the forces on one little cube of water. So you have a cube of water that's deep, surrounded by all the other water in the lake. And the size of this cube is going to be V. And we're going to take a coordinate system. We're going to have it be Z, and in these directions, the vertical direction is X and Y. Z is going to be going down. Now, the nice thing is that there's going to be no forces acting really, or at least no net force acting in the X and the Y direction. We're going to take hydrostatic water that's just sitting there. So let's focus especially on the forces acting in the Z direction. So let's imagine here's the side view of this cube. And we want to know the forces. So what forces are acting on this little cube of water? What would be one force? Gravity. Okay, so gravity is acting downward. And gravity is going to be mass times acceleration of gravity, g. And the mass is just density times volume. So we get density times the volume. What's the volume of this little cube? D cubed times g, 9.8 meters per second squared. But that's not the only force. Otherwise, all the water in the lake would be rushing down towards the bottom of the lake. What's another force that acts on this cube?
Normal force?
Normal force, yes. Another name that we can call it is just the pressure. There's a pressure from the other water, which is essentially a normal force. And there's a pressure that pushes up from the bottom, and there's a pressure that pushes down from the top. There's also pressures from each side. They're all going to cancel out. So what we're going to do is we're going to call this spot here Z, and this is Z plus D. Actually, no, I want to call this Z. Since going down is positive, this would be Z plus D. That's better. So there's going to be a force pushing down here, and that force is going to come from the pressure of the other water. So this is the pressure as a function of Z, so at height, at depth Z. But pressure is force per unit area, so what do we have to multiply by to get the total force acting on the cube? Area, which would be D squared. So we're talking about this face of this area up here, so D squared. And there's also a pressure pushing from the bottom. And that's going to be at a different depth, so P of Z plus D might be different than P of Z, and that also has to get multiplied by D squared. Now, we're doing hydrostatics. So hydrostatics means the water is just sitting there in the lake. It's not moving. So the total force is going to equal 0. So the total force is going to be rho v cubed g. That's going down, so that's the positive direction in our example. This one's also positive direction, plus pressure times d squared. I should include that as d. And then this one's pointing up, which in our case is the negative direction. So minus the pressure at z plus d squared. And all those forces have to add up to 0 for a hydrostatic situation. All right, so we have our force equation. Now, I don't know if you know where I'm heading with this, but what do you think is the next thing we could do? Anybody have a suggestion?
Set P of z plus d squared equal to the rest. You could at least get rid of the minus sign, but it's actually not the direction I was going to go. D squared.
Yeah.
Z, like by the second term?
Well, these two terms look very similar. Let's put these together. But oftentimes what you want to do is we work with things per unit volume. So let's begin by dividing out by the volume. And the volume is d cubed. So I'll divide by the volume, and this term would become rho g. And I'm going to move these two terms to the other side. So now I'm going to get pressure z plus d with a plus sign. It's on the other side, minus pressure z. And the only thing else is I divided through by d cubed everywhere. These had d squareds up here. So when you divide through by d cubed, you get downstairs a d. Now, does anybody see where this is going? Let us imagine what happens if you make this little cube really small. So you go to the limit as d goes to 0. What does this thing become as d goes to 0? Pardon?
Infinity.
Well, it looks like it's going to go to infinity, but as d goes to 0, these two pressures are going to be almost the same. So you're really going to end up with 0 over 0. But if the limit as d goes to 0, this is really the definition of the derivative. This is what it means to be a derivative. And if the pressure was changing instantaneously, then you get an infinite derivative. But in general, this becomes rho g equals dp dz. So, you don't use a whole lot of calculus in this class, but I do want you to remember what sort of definition of the derivative is. Here's a d here, but here's d there. As d goes to 0 here, this becomes p of z minus p of z. You get 0 over 0, but in the limit, that becomes the derivative. And this is our first differential equation that we're going to look at. And it's kind of simple because, as we said, water is nearly incompressible, meaning that rho is essentially a constant, meaning that the derivative of the pressure is just a constant. So it's a pretty simple differential equation. Anybody know what the solution for the pressure would be if dp dz is a constant? No, you could get, you will have the pressure changing with z. So what it's saying is the pressure changes with z as a constant rate. So I want to get an equation for the pressure at all different z. It might be 0 at one spot, but it's going to be a function of z. Well, the easiest way for me to do solve differential equations is to just guess a solution. I want to find a function of pressure such that when I take the derivative of it, I get a constant. What function, if you take the derivative of it, you get a constant?
Mx.
You get x, or in this case z. You just get something that goes linear in z. So you're going to get something that goes rho g z. And then if we take the derivative, dp dz, we just get rho g. And the z and derivative of z is just 1. And there could be some constant
associated with the pressure. If you define pressure is one of those quantities that you really usually define it relative to some other quantity, or some other position. So if you set z equals 0 to be the surface of the lake, this would then be the air pressure at the surface of the lake, and this would be the term that increases the pressure as you go down into the lake. So this would be how the pressure changes with distance. The pressure gets larger as you go deeper into the water. That's the key. And how much larger? Well, it increases as rho times g. So rho times g. We got rho, that was 1,000, and that was kilograms per meters cubed. And g, I said, is 9.8. I want to just round that off to 10. G is essentially 10 meters per second squared. That's the acceleration of gravity surface there. If you want to be real accurate, you can use 9.8. So that's 10 to the third and times 10. So that's 10 to the fourth, or 10,000 kilograms meters per second squared. Well, kilogram meters per second, F equals ma. Mass times acceleration, that's a Newton. So you're getting newtons per meters cubed. Or in other words, 10,000 newtons per meter squared to Pascal, Pascal per meter. So for every meter you go down into water, you're going to get an increase of 10,000 pascals in pressure. A little easier way to think about it is 10 to the fifth pascals. 10 to the fifth pascals is 1 atmosphere. This is 10 to the fourth pascals per meter. So you end up, if you could write that as 10 atmospheres per meter. For every, is that right? Yes, for every meter, no, I didn't write that right. 1 atmospheres per 10 meter. There, if you work out the unit conversion, you find that you get 1 atmosphere of pressure for every 10 meters you go down in the water. So if you swim down to the bottom of a deep pool, maybe 10 meters, it's a pretty deep pool. I mean, this is like 3 or 4 meters up to the ceiling here, so it'd be a deep pool. You'd increase your pressure by 1 atmosphere. All right. Now, the ocean is deep. Okay? The deepest part of the ocean is roughly the same as the highest mountains. I mean, the depth of the deepest part of the ocean is about the same as the height of the highest mountains. So we say about 8,000 some kilometers or meters for the highest mountain. It's about the same. It's about 10 kilometers in depth. 10 kilometers, that is 10 to the fourth meters. So if you go down 10 to the fourth meters, you're going to get, at the bottom of the ocean, about 1,000 atmospheres of pressure. Well, that's a big pressure. When you're making an airplane fly, I told you that they had a pressurized cabin. They keep the inside cabin at about 1 atmosphere that we're used to living in. The outside is nearly vacuum. It's not completely vacuum, but if you went up into low space Earth orbit, it would be. You have a 1 atmosphere pressure difference between the inside and outside the airplane. If you go down in some submersible to the bottom of the Marianas Trench in the ocean, you now have 1,000 atmospheres between the outside water pressure on you and your inside, which is kept at 1 atmosphere so we can move around and live there. So it's a big, big difference by a factor of 1,000 in how you design these submersibles that go to the bottom of the ocean compared to designing an airplane that goes up into the top of the atmosphere. It's a big problem making things that can dive, submarines that can dive deep down. They've got to have very strong walls, otherwise they just would get crushed. Now, it's a little bit interesting to look at the way animals have to handle these large pressures. Because if you go down to the very bottom of the ocean, you'll find that down there's life. There are these, at the bottom of the ocean, there are these thermal vents they come up through and releasing like a volcano almost, but they're releasing hot water, and there's life forms that live there. But there's huge water pressures they live in. The interesting thing is, if you're made out of water, then the pressure pushing in on you is going to be just balanced by the pressure of you pushing back on the water. And it's not that big of a deal to have real high pressures if you're made completely out of water. But it becomes a big issue if you have any air inside your body. For instance, if you have air in your lungs and you dive down, well, now you've got a bigger issue, because now your water in your body may be pushing back on the high pressure of the water outside, but the air is compressible. Same thing with air in your sinuses all throughout your body. So animals that live in the air normally, like us, and breathe air, have problems when you dive down to low pressure, to low levels in water, deep down in water, because any air in our bodies gets compressed. Animals that are made up entirely of water don't have much problem. This also means that aquatic animals that live in the water, have to be built very differently than terrestrial animals that live in air. Because we live in air, we don't have to worry about these giant pressures. We can have air pockets, but aquatic animals that live in the ocean have to have a very different kind of design. Okay. So, if you want to go diving, you're probably going to need scuba gear. Anybody ever been scuba diving? No scuba divers. Okay, I guess Michigan's not the best place to do scuba diving. But my daughter just recently went scuba diving in Australia, and she had to train for it. It's kind of an elaborate thing. Basically, you have air tanks that you carry on your back, and the air tanks come up and fit into your mouth. And the idea is that as you dive down below the surface of the water, the pressure starts increasing with depth. And you have a sensor that measures that air pressure, that water pressure, and then adjusts the air pressure out of your tank to just match it. So now you found this trick through this kind of feedback loop to keep the air in your lungs at the same pressure as the air of the surrounding water, and you can dive down really far and you can go scuba diving. So scuba diving requires a little bit of technology, and it's really, your life depends on that technology working. But if it does work, everything working properly, you don't have all these problems of diving down deep. But there's still some issues. Number one, we breathe oxygen. And if you had a tank full of just compressed air, as you went deeper and deeper underwater with the scuba equipment, you'd be breathing higher and higher concentration air, which means you'd be breathing higher and higher concentration oxygen. And oxygen is, in fact, toxic. You think it's something you need for life, and it is. But if you have real high concentrations, oxygen can be toxic. So suppose you get down at 90 meters, so almost a football field down below the surface of the ocean. You get down there, and you're going to have 9 atmospheres of water pressure, plus the 1 atmosphere of air pressure from the air above. So you have 10 atmospheres of oxygen instead of 1 that we normally breathe. So your oxygen concentration is 10 times the amount that you're breathing on the surface of the earth, and you have all kinds of problems. Does anybody know how you get around that problem? Anybody have a relative who goes scuba diving who maybe tells you about it? Well, you can bring 2 tanks, one with oxygen and one with some other gas like nitrogen. And you can have a gizmo that will mix the amount of oxygen to keep the amount of oxygen the same as we normally breathe. And the air, the gas that gives you the higher pressure becomes nitrogen, which is essentially inert gas that you don't breathe at all. So oftentimes when you're going scuba diving, you have to have 2 air tanks that you carry down. Your oxygen and some other gas like nitrogen or maybe helium or something like that that can keep the pressures right. Now, nitrogen is not entirely inert. One thing it can do is, well, first of all, it can act sort of an anesthetic. So if you go down and start breathing in real high concentrations of nitrogen, you can get something called the rapture of the deep, where you begin to get kind of mixed up and lose your ability to think straight because of the nitrogen. But another problem is as you breathe this high pressure nitrogen, it dissolves inside your blood, which is not a big problem until you come back up to the surface. And then it's like opening a can of pop. All that dissolved nitrogen will then come out, can bubble out and form little bubbles in your blood system. And those bubbles can then go down to your capillaries and block the entrance to the capillary and cause all kinds of problems with getting blood to your tissue. So that's called the bends. And the bends is a decompression illness that arises from the nitrogen, the high pressure nitrogen bubbling out of your blood. Now the way you can get rid of the bends is you can slowly come to the surface. Because if you give it enough time, if you give it minutes or hours even sometimes, the nitrogen can slowly come out and be blown out through your lungs, and you can get rid of it without the sudden bubbling into your blood system. And it can solve the problem. So scuba divers run into this kind of decompression issue. And this brings up one problem that comes when you're building bridges. Anybody here been to St. Louis? That's not that far away. Okay. Did you see the arch?
Yeah.
Did you see a beautiful arch-style bridge near the arch that crosses the Mississippi?
It's been a while. So.
Okay. It's called the Eads Bridge. It was the first bridge, one of the first bridges across the lower Mississippi, built back in the 1800s, I believe. So they were going to build the Eads Bridge, and they needed to put some arches that went down into the bottom of the Mississippi River, and they kind of put onto the bedrock down there. So here's the Mississippi River, and here's where they're the bottom of it, and they're gonna put this cement platform where they're gonna then build the arches from. So they had to work down here at the bottom of the river. So what they did is they took this thing called a caisson, looked like this, and you put it at real high pressure, high air pressure. Okay, so that's the air pressure. And people can go down a ladder and they come down here, and then they can start working down here, breathing air, working down there. The reason why water wouldn't come rushing in is because it's got the high air pressure, high enough that the pressure of the air holds the water back so it won't come in through the bottom into this place, and you're able to work down there. The only problem is you're breathing really high pressure air, so you've got all the same problems as you have with scuba diving. Now, one of the problems is when you go home, because there's a little air hatch here that's normally sealed, and when you go home after working all day down here, you come up here and you open the hatch and there's a sudden change. Usually there's an air chamber. You have one door and you open it and you go in here, and then you slowly release the pressure until you're at air pressure, and then you open the other door and you go out. And if you do that in, say, 30 seconds, what's going to happen is as you leave, you get the bends. And people started working on this Eads Bridge, started getting sick. So the guys in charge of the bridge said, oh no, all our workers are getting sick. So they sent a doctor down here to figure out what's going on. And when the doctor looked around all day and he went home, he got sick. So finally, after a lot of investigation, they figured out it's this decompression illness. And the way to solve it is to make the guys sit here and wait for 30 minutes in the airlock as the pressure slowly changes so they can go home. None of them liked it because that meant they had to sit around for 30 minutes. But it got rid of the illness problem. It's an example of physics at work. But suppose somebody here said, this is just open here. Here's the water. I want to take off and have a little fun today. So I'm going to jump out. I'm going to swim out. And they'll never know because I've clocked in already. I'm going to swim out and get out on this, go to a bar in St. Louis and have a good time. And then I'll swim back down here and I'll get back in and then I'll go clock out. There's two problems with that idea. Okay, one problem is that you're breathing real high pressure air. As you swim out and you go up to the surface, that high pressure air is now doesn't have the surrounding high pressure water pushing in, and basically your lungs would burst. And the way scuba divers get around this is they blow out. If you constantly blowing your air out of your lungs at just the right rate, you can prevent that, but it means you have to be exhaling all the way. And the other problem is the bends. You would get the bends unless you swam really slowly. And since this person wasn't going to use any special equipment, basically had as much time he could hold his breath till he got to the surface. So that person's bad idea to try to do that because they're going to get the bends and they're going to have problems breathing. It does bring up one issue in scuba diving, is that when you're scuba diving, the one rule that you should always obey is to keep breathing. Because the breathing is what equilibrates your air pressure in your lungs with the surrounding water. And if you get nervous and hold your breath for a while and go up 10 meters, you're going to have all kinds of different pressures between your lungs and the outside rest of the body, and you're going to get injured. So you keep breathing, don't even hold your breath for 15 seconds or something if you're changing elevations. And you go up and down slowly. Usually when you're scuba diving, they tell you, okay, go up 10 meters and then swim around there for 10 minutes. And then go up another 10 meters and swim around there for 10 minutes. So you have to be very careful to avoid the bends. They train you all this with scuba diving, and then you can go. The other thing that's interesting is when I was little, we sometimes got fins and a mask just to kind of swim around under the water. And the mask would kind of go over your eyes like this, and I could see better underwater. Well, a real scuba mask goes over your nose too. And it has to, because that's what equilibrates the pressure. So imagine if you took one of these cheap little kiddie masks and put it on and tried to go scuba diving, what's going to happen? Well, first of all, when you go down deep in the pressure, it's going to press on the mask, and the mask is going to get caved in. And worse, your whole body is going to begin to go up at high pressure because the water is pushing on it, and basically your eyes are going to bulge out of their sockets, or else the blood vessels in your eye are going to begin to break out. So it's really gross. So if you ever see a real scuba mask, it's got air placed for your nose too, so you're breathing into the region between the mask and your face, and then you're at the same pressure as the outside is. It's cool. So a lot of interesting things with scuba diving. It's just one example of hydrostatics and an influence of the physics on life. Okay. Questions about that? You guys ought to at least try some, or at least go to St. Louis, or go to somewhere. You can't just have no experiences here. Okay. I'm going to erase all this, and we'll talk a little more about some of the homework problems. Now, suppose you want to measure pressure. Here's one way to do it. You take a pan, and you put some mercury. Why mercury and not water? It's because if you use water, I'm going to put a tube in here, and you have to have a really, really tall tube. But mercury being more dense is a little bit shorter tube. So you take a tube that's closed on one end, and you invert it, and you stick it into the mercury. Okay. Actually, you take a tube that's filled up with mercury, closed at one end. You stick it in upside down into the mercury, and then you let the mercury level drop because gravity, and it'll drop down to a certain point, in which case now you have a vacuum inside. And it'll drop down until the pressure of the air pushing down on the mercury is just enough to raise the mercury up this tube. See, something's got to be holding it up against gravity, and what's holding it up is the air pressure pushing down and then transmitted through the mercury. And so the question is, how high is this mercury? This is all mercury in here. How high is this level of mercury? We're going to call that H. Well, it's what it's going to take to hold that up against gravity. So the pressure that's going to be required is going to be density of mercury times G times the height. That's similar to what we saw before. So if you want to measure the air pressure, what you can do is you can just measure the height of this column of mercury, and then you multiply it by G and the times the density of mercury, and you can get P. Density of mercury, by the way, is about 13 times, a little over 13 times the density of water. So this is water. Your H is probably going to be millimeters. You got a giant tube. All right, so let's see now what this means. If you had, suppose you did this and you found that H was just 1 millimeter. What sort of pressure does that correspond to? Well, pressure would be, the density of mercury would be accurate as 13.5 times 10 to the third kilograms per meters cubed. G, I'll be accurate this time, 9.8 meters per second squared. H, we said is 1 millimeter, which is 10 to the minus 3 meters. There you got 10 to the 3 and 10 to the minus 3, so those cancel. So that's 13.5 times almost 10. It's going to be somewhere around 135. In fact, it's about 132 by the time you take into 9.8. And that's pascals. So what you find is 1 millimeter, for every millimeter of height of the mercury corresponds to 132 pascals of pressure. So you now have a way to measure pressure. And so you could quote all the pressures in pascals by doing this calculation, but oftentimes people will just say how many millimeters of mercury, and you're left to do the conversion yourself. So another unit of pressure that people often use is 1 millimeter Hg, which is 132 pascals, which is another name for it is a torr. Basically, torr and millimeter mercury are the same thing. So why all these different units? I don't know, historical accident. But if you're interested in 1 atmosphere, that's going to be 10 to the 5th pascals, which is 760 torr, or 760 millimeters of mercury. Sometimes that's even given another name, a bar. So we've got bar, torr, millimeter mercury, atmosphere, and pascal. The only ones we'll probably be using are pascal mainly, and sometimes we'll use atmosphere or millimeter mercury. You can forget about torr and bar, but I just wanted you to know about them. Now, suppose you go give blood. They're having a blood drive pretty soon here at OU. Might be having one today, as a matter of fact. And they take your blood pressure, and they tell you your blood pressure is 110/70. What do those numbers mean? Anybody know what those numbers mean?
Systolic over diastolic.
Okay. When the heart contracts, called systolic pressure, it goes up, the pressure goes up, and then the heart relaxes, the pressure goes down. But what does the 110 actually correspond to? What is that?
Millimeters of mercury?
It's millimeters of mercury. So if I tell you your blood pressure is 110/70, that means, and this is usually relative to air pressure, so your pressure in your blood is 110 millimeters of mercury above air pressure when the heart contracts, and only 70 millimeters of mercury above air pressure when your heart relaxes. And those are the two numbers. And so that's one example where we do use millimeters of mercury when we're quoting the blood pressure. Okay. Now, suppose you want to figure out how high you're going to hang a bag of saline above a person who's lying in a bed in the hospital room, because you're going to infuse them with some drug through a saline drip that's coming down. Well, you can basically use this calculation. You calculate how much pressure you need. Now, you can't infuse somebody with just an infinitesimal amount of pressure above the air pressure. You have to have a certain amount of pressure to drive the fluid in. And one of the homework problems, I think problem 1.17, gives you the basically the pressure you're going to drive the saline at. And you really want the pressure above air pressure, because you're surrounded by air and it's pushing in with 1 atmosphere. So you have to have a certain pressure above that to calculate in order to hang the saline. So you can basically take this equation, but now use the density of water, and you can figure out how high the bag of saline has to be. So one of your homework problems is essentially using this calculation with water to calculate how high hang a bag of saline. I warn you, you're going to get an answer that seems awfully small, and that's in part because it neglected sort of the viscous resistance of the needle itself. So if you get an answer that seems like it's smaller than what you expect, you kind of expect to get somewhere around 1 meter, because that's what you used to see inside the hospital when somebody's got a bag hanging on a pole. You're going to get a little bit smaller, but it still will show you the basic idea. Another issue is standing on your head. So problem 116 talks a little bit, it's kind of a qualitative problem about standing on your head. And the idea is that our bodies are a vertical cylinder. And we have higher pressure down near our feet than we have near our heads. So our bodies have evolved so that the blood vessels in your feet can withstand very high pressures, because we're 1.5 meters of height, so we're going to have quite a bit of difference in your pressure. And the vessels in your head don't have to withstand that high of a pressure, so they tend to be a little more fragile. So now you go and you stand on your head. And so you're going, working, you're up on your head, and now you feel like your head's bulging. And the reason is, I'm practically answering the question for you, but it's a qualitative question. Your head's not used to these high pressures, and now you're at the bottom of a cylinder of water, basically, and you have a much higher pressure in your head than in your feet, and it feels uncomfortable. So now I have another homework problem for you guys. It's not an assigned one, but next time you go swimming, what I want you to do is first, on the side of the pool, I want you to go stand on your head, outside in the air, and you're going to feel like your head's bulging, your eyes are bulging out. Then I want you to go into the pool and swim down to the bottom of the pool, and I want you to stand on your head. It's going to be a completely different experience, not just because you can't breathe, but because now the water pressure is lower up here near your feet and higher near your head. It's just counteracting this effect of your cylinder increasing the pressure, and you're going to feel like your eyes aren't bulging out. So it's a very different, it shows what the different experience can be between aquatic and terrestrial life. You have to worry about pressure differences. That's also the reason why when you take your blood pressure, you stick the cuff right here at the height of the heart. If you took your blood pressure down here, what they really want to measure is the blood pressure in the heart. So if you took your blood pressure down here while you're standing or sitting, you'd be off by this distance. What is that? Maybe 20 centimeters or something. So 1/10 of a meter. 1/10 of a meter means instead of getting 110, you'd be getting something that's different by. It works out. 1/10 of a meter would give you 1/100th of an atmosphere. You can work it out. It would give you a difference, a significant difference. It wouldn't be doubling the pressure, but it would give you enough pressure that might make a diagnostic error when you're deciding if you want to give this person medication or something. So it's another example where this height doesn't. Okay, a couple more things I want to go over before we call it a day. I want to talk a little bit about buoyancy. And to understand buoyancy, we're going to rework that problem where we found the forces on the cube of water. But now we're going to have a cube of something that's not water. Okay, so this is going to be some object. Maybe this is you, or maybe this is a rock that you drop in the water or something. So we want to figure out all the forces. So we're going to go through this quickly. There's going to be a weight. And that's going to be rho, and this is going to be rho 0, because that's rho 0 is the density of the object, O, times G times d cubed, because it's density times volume into mass. But it's in water, and we know what the pressure density is for water. We know that there's a bigger pressure down here, pressure Z plus d squared, pushing up from the bottom, and P of Z d squared pushing down. Now this is not necessarily going to be zero force. You drop something in water and it can sink. So we want to find the net force. That's going to be rho naught G d cubed. That's the weight. And there's also going to be plus P of Z d squared. And then there's going to be minus, pushing from the bottom up, Z plus d squared. And that's the net force. Now, oftentimes we like to do things per unit volume. So force per unit volume is going to be rho naught G divided through by d cubed. And then we're going to get, I'll say, minus P of Z plus D, and then a minus P of Z. That way the minus and the minus would cancel. And when we divide through by d cubed, d squared, these are just a little d down here. So rho naught G minus, this becomes dP dZ. This is the definition of derivative as d goes down to 0. But we already figured out what the pressure was, in a lake in water. We found that this thing was just rho of water times G. That's what we found for our last analysis. So what you end up getting is the difference of the densities times G is going to be the net force per unit volume on this object. Sometimes this is called the effective density, the difference between the density and water. All right, so let's think now two different cases. First of all, let's consider birds. Birds are mostly made up of water. So their rho naught would be essentially the density of water. But they live in air. So really, I shouldn't call this H2O. That was one example. But in the case of a bird, the surrounding fluid is air, and this would be rho air. Rho for the bird, the tissues in the bird is going to be about 1,000 for its density. Air is about 1.2. So the effective density is going to be basically the density of water. So in other words, for the bird in air, this is a very, very minor effect. This is a less than 1% effect. When you're living in air, buoyancy plays almost no role. The force that you experience is essentially the force you experience from gravity. But now let's talk about a fish. A fish is made out of water. So it's made out of water, and the fish has water all around it, surrounding it. So you get density of water minus density of water, they cancel out, and you essentially have no force. So animals that live in water are almost neutrally buoyant. They're made out of water, and they are surrounded by water. So that they don't tend to sink or rise very much. They basically just sit there neutral. So that's called neutral buoyancy. And so life is very different for a fish than for a bird. For a bird, you're spending all your time fighting gravity to stay up in the air so you won't fall down. Whereas a fish, you just sit there, and all you have to do is move horizontally to get from one place to another, but you don't have to worry about going up and down because you're neutrally buoyant, almost at least, and it works. Now, this neutral buoyancy can be useful, for instance, when NASA trains its astronauts for working in outer space, where you're basically zero gravity environment. hard to train those astronauts before they go up into space. So what they'll often do is get a big pool, and they'll have the astronauts go down in the pool and work underwater with a scuba gear on. And that way they get used to almost a zero gravity environment. There's a slight buoyancy. If they have air tanks on, they might tend to rise. And what you can do is you can adjust, put on a belt with some weights and adjust the amount of weight just to make sure that their density is exactly the density of the surrounding water. And you can make the person neutrally buoyant. And that's the way they train the astronauts for working on, say, spacewalks. It's not exactly the same because water has viscosity that we'll talk about next class. So it's a little bit different, but still it allows you to get used to this neutral, zero gravity situation. So this idea of buoyancy can be important. Things way different underwater. Okay, one last thing I want to go over is a problem from the book. Not one on your homework, but one that shows this effect of neutral buoyancy. Okay, this is talking about swim bladders in fish. Now it turns out that fish, although most of their body is made up of tissue, which is largely water, they do have some bones and things. So fish have a density that's slightly higher than water. So the density of the fish's tissue is about 1030 kilograms per meter cubed, whereas the density of the surrounding water is about 1,000. So a fish would be almost neutrally buoyant, but if you just let it sit there, it would slowly go down. So you need a way to prevent it from going slowly down because of its bones and other things. So what fish have done, many fish at least, they have a little air pocket inside them, almost like little lungs, but they're not really lungs. And remember, air has a density of 1.2. And now the question is, how big of an air bladder, that's what these things are called, do you need in the fish in order to make it neutrally buoyant? Well, let's say the fish itself has a volume V and the air bladder has a volume U. What you want is the net density. So your average density of the fish plus the air bladder. And you want that to exactly match the density of the water. So the total density is going to be the total mass of the fish plus the air bladder divided by their total volume. So the mass of the fish is going to be V times the density of the fish. And the mass of the air bladder is going to be U times the density of the air bladder. So each of these is density times volume or mass. And you're going to divide by the total volume, which is just V plus U. And you want to set that equal to, it's going to be its average, and you want that average equal to 1,000. And then you're going to be completely neutrally buoyant. So this is, even if the fish is not exactly at the same density as water, you can make it with neutral buoyancy using the air bladder. Okay, so let's see if we can finish this. The volume we're really trying to find is the relative size of U and V. So you want to say, does 1% of the fish's volume have to be air, or 10%, or what? So we're going to take 1,000 equals V times the fish's 1030 plus U times the air is 1.2 divided by V plus U. We want to solve essentially for the ratio of V over U. So multiply through by V plus U. 1,000 V plus 1,000 U equals 1030 V plus 1.2 U. All right. We'll take the 1,000 off of both sides. That'll give us 30 V. We subtract 1,000 off. And you'll take the 1.2 off both sides. So that'll give us 998.8 times U.
which is pretty close to the original 1,000. And then you can calculate U equals 30 over, this is essentially the same as 1,000, so I'll just round it off. V, or in other words, 3/100ths times V. So what it says is that only have to use up 3% of the fish's volume in an air bladder, and that can make you neutrally buoyant. So many fish have a very small air bladder in them, and that can allow them, as they adjust that amount of air in the air bladder, they can adjust to be completely neutrally buoyant. These air bladders eventually evolved into our lungs for fish that came out of the ocean and crawled around. So it's interesting. This is kind of like calculating the buoyancy of our bodies. Our bodies have air bladders, that is our lungs, and usually our density is a little bit less than the density of water. So we tend to float. So dead bodies will float until their lungs fill up with water, and then they'll sink. And that's another example of this effect. Okay, so that's it for today. Remember to bring questions about homework Wednesday, and we'll talk about viscosity.